So we were discussing this special kind of beam which is fixed to the wall, and this particular configuration is referred to as the cantilever beam. And it was subjected to this kind of uniform loading on its top surface. In the last class, we had completed up to this part where we had found out the expression of the shear force after taking a cut section, which was this orange colored cut section, and by taking the cut part which was to the left of it. So this white rectangle you see here, that is to the left of this cut section, and we were finding out the shear force, and today our plan is to find out the bending moment on the right hand side portion of this cut part. Please also note that this force V, the shear force V, that is pointing downward, accepted in the last class. If you refer to the textbook, and in fact most of the textbooks, you will find that this same positivity convention is accepted. So on the right hand side portion of a cut part, the downward pointing force is considered to be positive. It may come out numerically to be negative, but this thing is considered to be positive downward, and this anti-clockwise sense is taken to be the positive sense of the bending moment. All right, so today we will try to find out the bending moment. So for the bending moment, you tell me quickly what I should do. In the previous example, we have already done a similar kind of thing. So
we consider moment across the cut surface at that point.
Right. So we considered the balance of moment about an axis which is passing through. So on this side, okay, you take an axis which is passing through this right hand side, and we take the moment about that. So if we do that, so sigma m is equal to 0. I'm of course referring to this diagram. Okay. Tell me what should be the contribution from this blue part.
Omega square by 2.
Wx square by 2.
Why is it omega x square by 2?
Sir, sorry, omega and W.
So Wx is the force and the...
Right. So the people who are saying this, are you from the autumn semester or are you from the spring semester?
So spring semester.
Spring semester. Good. Okay. So it's like this. What you are saying is perfectly correct. So the answer the students gave, I'm repeating that answer for the benefit of the other students. They initially said omega because my W is not looking very nice. So probably they thought that this is omega, but this is W. Okay. So W into X. W is the force, the external force applied per unit length. The total length under consideration here is X. So the total force here is W into X. Now, the answer they gave for the moment was Wx square by 2. They're saying that because what they are thinking is Wx is the total force, and that total force, because this force is uniformly distributed, it is effectively acting at the midpoint of this cut part. Midpoint of this cut part is at a distance of x by 2 from the left end. Equivalently, it is a distance of x by 2 from the right end. So this is the net force that is acting here will be acting. So if you're thinking in terms of equivalent forces, it will be acting at the mid part. So it is something like x by 2. And this is perfectly correct. So we can actually write this as W into x square by 2. Whether it is positive or negative, tell me.
So it is positive according to the convention.
Positive, sir.
Considered.
So we have considered this anti-clockwise sense to be positive. So Wx square by 2. What is the other contribution by considering the balance of moment here?
M.
Plus M.
Plus M. So this is equal to 0. so that our answer for the expression of the bending moment, please understand, okay, that when I'm writing this sigma m, I'm actually thinking, so this m and this m, they are not the same. So maybe, I mean, you consider it to be some kind of a generic m. Okay, this has, I mean, this is not the same as this. So this is something like sigma mz, okay, where mz represents the balance of moment about an axis which is parallel to the z-axis, and the z-axis is coming out of the plane of the screen. So this m is coming out to be minus wx square by 2. As far as the solution of the problem is concerned, we are done. Okay, done means if you want to draw the shear force diagram, it will be like this. The abscissa is the x and the ordinate is v, and since this is v equal to minus w into x, where w itself is a constant, it will be simply like this. Okay, where the maximum value that you are obtaining here, what is this value?
W
Minus
into L.
WL.
W into L. Okay, this is the magnitude. What about the shear force? Sorry, the bending moment diagram?
So
Inverted parabola.
It will look like a parabola. Okay, it will look like a parabola because the expression for m is indeed like a parabola. Okay. Now, what is the largest value of this, largest magnitude of this?
WL square by 2.
WL square by 2. Now, these are the kind of things which you should particularly note. See, for this easy example, it is, I mean, the expressions are coming out in a very simple fashion. V is minus Wx, M is minus Wx square by 2. Everything is nice and easy. However, in a more complicated situation, and we are going to address some of those complicated situations, you will see that drawing the shear force and bending moment diagram, it will still be easy as far as the intellectual effort is concerned, but it will be a little bit time consuming because you will have a number of different parts of the beam which are subjected to different kinds of loads. As a result, what will happen is that it may not be immediately obvious to you where the largest magnitude of the bending moment is occurring or where the largest magnitude of the shear force is occurring. And it is those kinds of things which we may ask you in the examination. And it is not just for the purpose of teasing you in the examination. Those are the kind of things which you as a professional engineer will also have to keep in mind. And that why you have to keep in mind, that will become even clearer when we go on to the discussion in our next week. When we go on to discuss the various kinds of flexural stresses, you will see why that is important. Okay, so you have to not only be concerned with the expressions or the values of the bending stresses, but you will have to find out the maximum possible value of the bending stresses. And since the bending stresses will involve in their expression this m, that is why you will have to find out where in the beam the largest value of the bending moment is, correspondingly where the largest value of the bending stresses is, which will actually help you to design the beam. So we'll go into those kinds of discussion, but just wanted to motivate it. Now, another point which I want to highlight here is that you see here it was a uniformly distributed load, and here you were immediately able to almost visualize why this kind of a thing would happen for the calculation of the bending moment. But in a more general situation, it is very much possible that this distributed load, it is not uniform. Okay, it is very much possible. In fact, we are going to take up an example just a bit later where the distribution of load will be triangular in nature. But why just triangular? It could be quadratic or it could be completely non-uniform. So what do you do in those kinds of situations? So you actually have to do a proper integration in those kinds of situations. So let me, for this simple example itself, let me discuss very quickly what happens or how do you go about that integration. Okay, so let me go to the next slide and redraw this cut part. Please note again that this is not the entire beam. This length is x. Over this length, I still have the uniform distribution, but I want to pretend that I do not know a priori how to find out this wx square by 2. I want to go through a formal step-by-step procedure or a more general step-by-step procedure such that even if the distribution is not uniform, I should be able to find out the contribution towards the bending moment. Okay, so for that, what I will do is I will consider within this length x, okay, within this length x, a smaller strip of length, let's say dx dash. So dx dash is a new variable that I am introducing. I think it will be better if I zoom into this thing a little bit. Okay, so this is my dx dash. Please note that this x dash is a completely separate variable from this x. Okay, so x is like the length under consideration. X dash is the variable which is going to cover from 0 to x. But what I mean to say is that this particular distance here, that is x dash. Okay, so as I move this strip from this end to this end, I will be covering this entire distance x. Now you tell me with respect to this, what will be the contribution of the what will be the contribution to the bending moment as a result of the distribution of forces which is acting over this small strip dx dash. We are again considering this kind of this thing, right? This is our m, still this is our v.
W dx dash x minus x dash into x minus x dash.
W into dx dash, that is the force which is acting over this infinitesimal strip. This is the force. Now I want the moment arm. I'm taking the moment about this right hand side. Okay, about the axis which is through this right hand side. So if this distance is x dash and this distance is x, so naturally this distance should be x minus x dash. I hope it is clear to everyone. So the moment arm for this is x minus x dash. And this thing has to be integrated from x dash is equal to 0 to x dash is equal to x. All right. And please note that the sense of this moment is very much anti-clockwise. So it is coming with a positive sign. So overall, the balance of moment equation will be like this. And now you verify that if you calculate this thing, it is actually going to come out to be equal to x squared by 2. Okay, you can actually check this out. The answer to this will be what? This will be minus w x minus x dash square by 2, where the limits of integration here will be 0 to x. And if you put in the limits, the first one will be 0 and the second one will be wx square by 2 with a minus in front, but there is another minus in front. So overall this will come out to be plus wx square by 2. You can verify this yourself. Okay, so overall m is actually coming out to be this minus wx square by 2, which is exactly what we had found out in the previous page. So you see, m was coming out to be minus wx square by 2. Here also it is minus wx square by 2. But please note that this is a very general enough thing. Nowhere in this derivation we have used the fact that this is a uniformly distributed load. So whether it is a triangular load or quadratic load or whatever other kind of load or whatever other kind of distribution, you can still use this method to find out the contribution to the bending moment. All right, now let us take a look at another example. Slightly more involved situation. We again have a cantilever beam. So this part that you are seeing, that is our beam, which is again firmly fixed to the right hand side wall. On this beam, so this cantilever beam is subjected to this uniform distribution of force, which is of strength or intensity, W. Again, W has the unit of Newton per meter. But unlike the previous example, the uniform distribution of force is only acting from this part to this part. Furthermore, you see there is a slight projecting out of the beam of a member like this. Now, this member, although it may seem that it is making the overall structure to be very complicated, but in reality, what happens is that these kinds of structures, the contribution to the mechanical system itself is quite negligible. In the kinds of situations where these are not negligible, they are actually referred to as frames. They are out of the syllabus. Okay, so we don't have to worry about that. However, you don't have to have any kind of knowledge regarding frames, what to neglect, what not to neglect in order to solve this problem. Your job here is to find out the distribution of shear force and bending moment all throughout this, throughout the length of this beam. Now you tell me, and you will be able to answer this if you have gone through the first few pages of the textbook. How do I go about solving this problem? What do I do? Because this part here, you have to accept it is an extra complicating feature.
So can we replace a force P at the point A plus B?
I have to replace the force. So you are talking of taking some kind of an equivalent force system, right?
Yes, sir.
Yes, that is the method actually. So see, this problem would not have been anything special, and I would not have been discussing it separately had this part not been present. So suppose you had been given, instead of this kind of a situation, suppose you had been given just a simple cantilever beam like this, and then over it there was some kind of a distribution of forces just like this left hand side. There is no difference here, and instead of the force being acting here, perhaps it was directly acting here. So in that kind of a situation, sure, the drawing of the shear force and the bending moment diagram would have been a little bit more complicated compared to the previous two examples that we have taken up. But in terms of the conceptual understanding of how to tackle this problem, there is practically no difference between what we are doing here, what we would be doing here, and what we would be doing, what we were doing in the previous two examples. But there is a little bit of a difference. You see, this force is being applied here, and I am suddenly translating that force from here to somewhere here. Okay, so you understand that this part is A and this part is B. So when I'm translating this force from here to here like this, what else do I need to do in order to ensure? Yes,
A moment, couple more.
Yes, good. But let me finish my sentence. So as I was saying, what do I need to do to ensure that in going from this force to a force that is being applied here, as I have shown here, these two systems are actually equivalent? That can be ensured only if I take a corresponding moment which was being contributed by the presence of the force here. And what is the value of that moment? We can understand it by taking the moment of this force about the point to which we want to translate it to. I repeat, we can take the equivalent system by considering the contribution to the moment that this force was contributing to by taking the moment about the point to which we are translating. Okay, so this is our source, this is our destination. Take the moment about the destination. So this is our destination. We have already arrived at the destination. Now we have to pay the, like it is almost like paying the rent for going to the destination, or paying the bus fare in order to go to that destination. So what is the value of that moment? Value of that moment is c times p. And what is the sense of that? Sense is anti-clockwise. So this value is c into p. There should not be absolutely any confusion about it. Okay, now in order to proceed with this, what do I do? You tell me.
So we will have to separate it into different sections.
Exactly, exactly. So,
Sir, excuse me, sir.
So the
Sorry?
moment should be clockwise, no?
Yes, sir, clockwise.
Yes, sir.
let me check. So I'm taking, right, you are absolutely right. I made a silly mistake. Sorry. Thank you. Okay, so this is our moment arm. The rotation is like this.
Want also.
Sorry?
So can we shift that P force to any other point and taking moment like that?
Absolutely. You can shift P to here also, no problem. As long as you take the correct moment, there is no problem. So if you shift P to this point, what will be the moment arm? A plus B plus C. So you will have to write that as A plus B plus C into P if you translate this P to here. Okay.
So suppose if I shift that point P exactly below, then
Exactly below.
so then moment will be 0 again. Means how it can be done? Actually, I'm not getting.
So that's the thing. So when you are saying that if you want to translate this P to here, effectively what you are saying is that you are completely neglecting the presence of this thing. That is a little bit problematic. Okay. However, when we are translating this force to this part, we are kind of moving to a point where you are kind of separating the beam and this little inverted L-shaped kind of thing, and considering the influence of this L-shaped part on this part. Okay, so effectively what you are doing here is like separating out that L-shaped part and considering the entire influence of that L-shaped part that it was having on this beam. And now we are trying to solve this thing. Okay, so had this part been extremely small and negligible, it would have made some kind of sense to completely neglect its structure and take just the application of this force. But in this kind of a situation, we cannot really neglect that.
Sir,
Yes.
sir, if the L-shaped part is separated, sir, like we are separating the L-shaped part, so like the moment of P will be PC in the anti-clockwise direction for the L-shaped part. So
Yes.
it should be clockwise for the bar.
What?
So like the moment PC will be anti-clockwise for the L-shaped part. If we draw both L-shaped part and bar separately, then the moment for the L-shaped part will be PC in the anti-clockwise direction. So like the bar will have the opposite moment.
Let me see what you are saying. You are saying that suppose I actually separate it out like this.
Yes, yes, sir.
And I want to draw the free body diagram of this. right? Okay. And now you are saying that now, of course, I will need to have a reaction force like this.
Yes, sir.
And what will be, so there is a couple associated with this. This couple is having, this couple is having,
Anti-clockwise.
no, this couple is having the sense of clockwise. Is it not? The couple due to this,
So
these two
couple will be
forces.
anti-clockwise.
Okay, sir. Yeah,
No. So what I'm saying is forget about reaction forces. Suppose you have this P force and this P dash force, then the couple due to these two forces, that is, and this is clockwise, no?
Yes, sir. But the
So now listen. So the couple due to this is like this. Okay, remember that. Now this thing here is like this. This is the thing that I have just drawn, this curved arrow that I have drawn. This is the reaction force reaction couple exerted by the beam on this L-shaped part.
okay.
Yeah, so this is CP. Correspondingly, there will be an equal and opposite couple exerted by the frame on this beam, that is of the opposite sense, which is like this. So it is correct. But very good question. I like this kind of discussion. Okay, so you understand that we have practically taken this original mechanical system, we have taken an equivalent form of that mechanical system. This is an extremely important part, which is why I made it a point not to discuss this as part of a bigger problem, but rather to discuss this particular conceptual thing separately. Okay, you will see that in quite a few other problems, I think I have put one question like this in the tutorial sheet also, but in many other situations, you will have to draw this kind of an equivalent system. In fact, you can also have situations where there is such a complicated structure here on top of the beam where to the wall some kind of cable is there, some kind of complicated loading is here, that cable could be under tension and it could be having some kind of an oblique force. So all sorts of complications are there. Now even if that is there, as long as you are being expected to find out the shear force and the bending moment, don't get afraid. You just have to simplify the situation by taking an equivalent force system. So you see, in terms of these aspects of this particular chapter, the actual intellectual effort that you have to give in order to solve this problem is in terms of finding out the reaction forces correctly, the reaction moments correctly, the various kinds of equivalent systems that you have to do. So effectively, you are basically doing first year mechanics problem. The rest of it, finding out the shear force and the bending moment expressions and subsequently drawing the shear force and bending moment diagrams, sure, that is very much part of your second year syllabus. That is something slightly advanced and there are sophisticated notions associated with it. But in terms of the actual execution, the real effort that you have to start out with is exactly like your first year problems. Okay, so all of you, I especially emphasize this, you cannot afford to forget what you studied during those classes in your first year. If you feel that you need to revise them, go back and revise them. If you do not, it will come back to bite you. Okay, it has happened to me, it has happened to many of my friends that we kind of neglected what we studied in our first year, and then it did come back to bite us in second year, in third year, and then we actually had to go back and revise and we had to correct our deficiencies.
Sir, in any kind of means complicated things, if given like cables and so, sir, we can directly consider the equilibrium of this cantilever, no, directly.
You isolate out the cantilever, not just cantilever, it could be a simply supported beam also. So you separate out the beam and consider the various forces and moments that are acting directly on the beam as if no other thing is present.
Sir, like if if a cable is given and the tension in that cable is unknown, then for getting out that tension, we need to consider the equilibrium of this beam first.
Yes, yes. Not just the beam. Then you have to consider the equilibrium of the whole structure. Find out first the tension in the beam, and then in the next step, in the next intermediate step, you'll have to consider the beam in isolation. Consider the effect of the tension on that beam. Draw the equivalent force system, force couple system, and then proceed with the shear force and bending moment. You will see. Okay, so let us not, discuss everything in abstract and without going into specific problems, but those are the kind of things you will definitely have to do. Okay, so without investing any more time on these abstract discussions, let us proceed with the general thing. You see, for the actual solution, I will not go up to the actual drawing of the bending moment, shear force, all those things, but you understand at least that for solving this problem, what I will do is I will consider first the part, so for x lying between 0 and a. Okay, and when I'm writing this, I'm actually referring to this diagram, okay, on the right hand side. So for x lying between 0 and a, what do I have? I have v is equal to, so you understand that what I'm doing here effectively is first taking a cut section which is here. Okay, between 0 and a. So what is the v here now? Tell me quickly.
Minus w into x.
Minus w into x. What is the expression for m? As long as x is between 0 and a. So you can quickly draw
minus omega x square by 2.
Yes.
Minus wx square by 2.
Exactly. So again, you have the same kind of diagram which we were doing previously. Now this distance here is x. Okay, this is w. So the situation is exactly like before. We have this m here, this v here. This v we have already found out to be minus wx, and m, just like before, it is minus wx square by 2. That's it. Next, for x lying between a and b. So now what we are doing? We are taking a cut section in this part. And now for this, the diagram will be like this. Where the full distribution or the full contribution from this distributed load is coming into the picture, unlike the previous case where each time it was a little bit increasing because of the variation in x. Between A and B, there is no force. There is no extra force. You see, between A and B, nothing else is there. All right. So now you tell me what should be the expression of the V.
So w
Minus w into a.
W.
Minus WA. Very good. So please note that I am considering this diagram again. This is V, this is N. What is the expression of M?
W
So minus wax plus wa square by 2.
So you can think of it again like this, that this entire contribution, since it is coming into the picture, the total force due to this is W into A. This is W into A. This is the total force. Now we have to find out a moment arm associated with that force. This force, since it is associated with a uniform distribution of load, it may be understood to be acting at the midpoint over its distributed area. So its distributed thing is over this length 0 to A. So we can understand that if we were to take an equivalent force, it would be somewhere here. That would be the equivalent force. That will be of magnitude WA. Since it is at a distance of A by 2 from the left end, what will be the distance here? This moment arm?
X minus a by 2.
X minus A by 2. So I think one of you actually gave the correct expression of this, but in a slightly different way. So I think this way is quite intuitive to understand. It will not be difficult. If you find thinking in terms of these kinds of equivalent forces difficult, then you can definitely do each time the integration thing. Okay. So when I was younger, I preferred that. Okay, doing integration. Of course, it was quite unnecessary. I think this is much easier to think about, but I mean, to each his own. All right. However, I will like to point out certain things here. I have been getting certain messages from students requesting me to suggest textbooks or some kinds of books which will help them to prepare for GATE or other kinds of this objective type engineering examinations, which we usually sit for maybe in your last years of your studies for Indian engineering services or things like that. So usually IITians don't go for those kinds of things, but there are equivalently a few IITians who are still interested in that. For those kinds of examinations where the time management thing is very, very important. So at that level, again, you will have to get into the mindset that you had been getting into during your JEE preparation. So you will have to try to answer the maximum possible thing in the minimum possible time. So in those kinds of situations, if you try to do it in a very general fashion, then you will be at a loss. For those kinds of examinations, yes, you will have to definitely take recourse to these kinds of things. Okay, where you minimize the time required to solve the problem. All right. So we have covered up to B. Beyond B, what do we do? So for X lying between L and B, please understand that this entire length is L. Okay. I think I made a mistake in drawing this thing. Rather stupid thing. I'll correct it. Okay. So this distance is A, but this total distance is B. Okay. And this total distance is L. Otherwise, what I have written here, it doesn't make any sense. All right. Now you tell me for X lying between B and L, I am considering a cut section in this portion. Now, when I am considering a cut portion in that section, you understand that force P and the couple that I had drawn, that will come into the picture. Sorry.
So actually there should be X from B minus A to B.
Sorry?
For second part, so second section actually.
Yes.
It should be B minus A to B. Actually we are seeing that part now.
No, X is lying between A and B. Think about it.
Yes, sir.
Yeah. Okay, so I have my P present somewhere here, and there is a couple of value CP also present here, and I have this force V here and this moment here. Now you tell me, what will be the expression for V?
V is equal to minus P minus WA.
Right, so this will be like V plus P plus WA is equal to 0. So this gives us V is equal to minus WA minus P. This was easy enough. Next, for the moment, you write it properly. Okay, so I'm writing out this M first, which is this M. And again, I'm considering the anti-clockwise sense to be positive. So this is plus M you tell me what is the contribution from this one. That will be minus Cp.
Minus CPS.
Yes. What will be the contribution from this force P?
P times X minus B.
P times x minus a minus b.
P times
X minus B.
X minus B. Right.
X minus b.
Yeah, because this diagram is also incorrect. No, I have corrected that now. This entire thing is B. Okay. This is positive or negative? I've written this is negative. This is incorrect, no? This should be positive. Yeah. What else?
Some moment due to this
Distributed force.
Distributed force. The total force here is WA.
Into x minus a, right?
Yes.
x by
And then into X minus A by 2.
x minus a.
Yeah. And what is the sense of this?
Positive.
Positive.
Anti-clockwise.
Anti-clockwise, which means according to our accepted convention, this is plus. So this is equal to 0, and now you can find out the expression for M. Okay, so M is equal to plus Cp minus P x minus B minus WA into X minus A by 2. That's it. Now you see that in the first part, this M was coming out to be a quadratic kind of expression. In the second part, it is coming out to be something linear. In the third part, also it is coming out to be something linear. I think someone has unmuted their mic. Please mute yourself, okay? Please mute yourself. Thank you. In the third also, I think the student is not realizing. Let me check. Karan, I think you are unmuted. Okay. In both the second part and the third part, we have this linear dependence on X, but in the first part it was quadratic dependence. However, there is difference in the y-intercept of this M expression. Okay, so the diagram will certainly look quite complicated, but as far as I mean, it's just hard work. Okay, in writing down these expressions or drawing these expressions, the actual intellectual effort that has already been done here. All right. Now, what I would like to do is to quickly cover a triangular load. So this is the thing. Unlike the previous two examples where I was considering a cantilever beam, now I am considering a simply supported beam, just for some change. Okay, it might as well have been a cantilever beam. Okay, for this kind of a situation, what do I do first? So again,
So we find the equation corresponding to distribution of force.
Wait. So here the question is again like before, that we have to find out the shear force and the bending moment diagrams. So we have to go from the left hand side to the right hand side of the beam. Okay, the only complication present here is that the distribution of load is triangular in nature. No other apparent difficulties here. So it seems like a straightforward thing to do. However, there is a little bit of a difference compared to the cantilever example. Can you point me that out at the very outset without writing any equation, anything, just by looking at the situation? Can you tell me what is the difference compared to
We cannot put the
There
equation
is no free end.
equal to half.
I could not hear you.
There is no free end.
There is no free end. That is the complication. In fact, we have addressed this kind of a situation earlier. Let us go back. So this was the first example that we had considered. This was our example number 1. Very simple kind of thing. So here it was, we had simple supports at both the ends. So the first thing that we did here was to find out the reaction forces at the two ends. The situation here was so very simple that you barely realized that you had to do this work. There was a force F very nicely symmetrically placed at the center point of this beam, at the midpoint of the span, and that led to this kind of a equal distribution or equal division of the reaction forces P by 2 and P by 2. So it was, even without writing any equation, we were able to do this. Now the problem that we are going to do now, this one, it is exactly the same kind of situation conceptually. The only difference is that the load is distributed in a different fashion. So our first job is to actually find out the reaction forces. Okay, we have to do that. Let me draw it here. Okay, there will be some reaction force here. Let's call this A and B. And let's call this as RA and this will be RB. Please note that this here is a hinge joint, and at the hinge joint, as per your funda from first year mechanics, you are supposed to draw one vertical reaction force and one horizontal reaction force here. So very theoretically speaking, we are supposed to find out one horizontal reaction force also here like this. But you can immediately understand that if you do sigma fx equal to 0 for this entire problem, there is no other horizontal force present. There is nothing externally present, nothing internally present. So it is bound to come out like this, that HA is going to be 0. So we don't have to consider this part. Okay, so now you are in your second year level, you don't have to do these kinds of obvious things, I mean, time and again. Please note that on the right hand side, you have a roller joint. It's a roller, I mean, pinned end, but with, I mean, it's a roller kind of thing. So here, there is absolutely no chance of any horizontal force appearing, because the presence of this roller indicates that there is no resistance to the horizontal motion of this or the horizontal displacement of this beam. Since there is no resistance, it means that there is no force, no reaction force in the horizontal direction, which is why you have, theoretically speaking, two reaction forces, two unknown reaction forces here, the RA and the HA, which I had indicated here. Two reaction forces here and one reaction force here. In total, you are dealing with three unknowns. And because this is like a 2D problem, you will be able to use the static equations of equilibrium to solve for these unknown things. In fact, you have implicitly already used one of those equations, that is sigma fx equal to 0, to ensure that HA is equal to 0. Okay, so this is very much a statically determinate problem still. Okay, had there been another support here, then this problem would have become a statically indeterminate one. We have already discussed this earlier, but these are important things, which is why I keep on revising them. All right, now we are in this kind of a situation. Question is, how do we find out RA and RB? Just tell me.
The force balance and momentum balance.
So torque first, torque about point A.
Yes, yes. So something like that. So we want to find out the expressions of RA and RB in terms of this given W. Please note that when I'm drawing this kind of a triangular distribution and I'm indicating by this W, what I mean to say is that the value of this intensity of force or the strength of this force per unit length at the right end at B, that is where it is W. Okay, at the left end it is 0. So it is linearly increasing from 0 Newton per meter to W. All right, these things are quite obvious to many of you, but to some students there may be some point of confusion. That is why I'm re-emphasizing these things. All right. So as one of you are, quite a few of you are mentioning that in order to find out RA and RB, I have to individually take the moment balances about the left end and the right end. So for RB, I have to take the moment about this end. I'll be able to find out RB. And if I want to find out RA, I can either do a force balance after finding out RB, or I can separately take a moment balance about this, whatever. That is why that is not the reason why I have taken up this problem. I know all of you can do these things. The reason why I want to address this is to find out if there is some possibility of finding out an equivalent position for this kind of a distributed load when I have to deal with the moment. What I mean to say is that earlier, when it was a uniformly distributed load, that is, when this W was constant all over the beam, you were immediately able to tell me that the equivalent placement for the force will be at the midpoint. Question is, can we find out such a equivalent position for this kind of a distributed loading, for this kind of a triangular loading also? So what we'll do is, we will consider it generally, okay, as if we don't know anything. So what we'll do is, we will we'll do the integration kind of thing. Okay, we'll do the integration kind of thing and then we'll see what it gives us. Okay, so tell me what I should do. So I want to find out RB. I will take the moment about this. So tell me what I should do.
So consider a small piece of length dx.
I will consider a distance dx. Okay, I will consider distance dx.
So the force per unit length for that particular dx will be Wx by L.
W by L into x.
X.
Yes, W by L into x. So yes, you understand that at any position x, so at any position x, the intensity of this distributed load will be W by L. So actually what we are writing here is that W minus 0 by L. Okay, the value here is W, the value here is 0. So it is W minus 0 divided by L minus 0. Okay, something like that. Basically linear interpolation. W by L, and now we are going up to a distance x. So it is W by L into x. Simple unitary method. Okay, like high school. This is the intensity at a distance x. So when we are taking the moment about the point A, I will consider this intensity. Okay, step by step we are doing. First of all, we are writing the intensity. This intensity is acting over what length?
dx.
dx.
It is acting over dx. We wish to find out the moment about which point? About the A point that I have written. So what is the moment on?
X.
Yes. So this distance here is x. This one here, it is dx. So W by L into x, that is the intensity, multiplied by the length, this is the force. And that force, this entire thing is the force multiplied by the x, that is the moment about the point A. And this thing has to be integrated from 0 to L. That is how you take into account the entire contribution to A. This is, so if I consider this to be this anti-clockwise to be positive, then this is minus or plus?
Positive, sir.
Positive, sure. I'm taking about A.
Okay, then it will be
Sir,
negative.
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 Negative,
Yes.
yes.
Then negative.
Negatives.
Yes. And what is the contribution to the moment by this force RB?
RB into L.
RB into L. Of course, we understand this entire length is L. RB into L. That is positive or negative?
Positive.
Positive. Okay. All right. Now, this is basically telling us like this. Sorry. RB into L is equal to, what is the thing that I'm getting here? W by L. This is within integration, this is x square. So this will be x cube by 3. So it will be L cube by 3. So this is coming out to be W L square by 2, but okay, let me W L square by 3, but I want to write it in a separate fashion. Okay, I'll do this in the next step. Left hand side, I'm keeping it. I'm not cancelling any L or anything. Okay, you'll see in a moment why. You see, what I have basically done here is to account for the contribution due to this distributed loading about this point A. I'm taking the entire moment of this distributed loading about the point A. This is that answer, WL square by 3. But I want to rewrite this answer in such a fashion which will allow me to understand it in terms of a force times a length. The force that I want to write it in the way is that what is, you see, what is the total force due to this thing? What is
WL by 2.
It is WL by 2. So you can very easily understand that had this been a distributed loading, uniformly distributed loading like this, had it been like this, it is not like that, but suppose imagine for a moment that it is like that. Okay, so it is like this. Then the entire thing would have been W into L, but now it is just the half contribution from it. So it is WL by 2. So WL by 2 is the total force which is being exerted due to this triangular distributed loading. If I write like this, in order to adjust with this expression, what do I have to do? I have to write this as twice L by 3. Okay, so you can understand that this is the force, this is the moment arm. This moment arm is calculated with respect to which point?
With respect
A.
to point A.
With respect to point A. Remember this, okay? So this is with respect to the left hand side. Okay, the A point, which is at the LHS. So when you have a distributed loading like this, okay, the moment arm corresponding to this end where it is like this, that moment arm is twice L by 3. Okay, this is an important result which will actually help you to solve certain problems quickly, where this distributed kind of loading, this kind of triangular loading is not the entire thing, rather it is part of the problem. Okay, next, suppose I were to ask you to find out the contribution to the moment calculated about the point B, then what would have, what do you think the answer would be?
WL square by 6.
So WL by 2 into L by 3. Okay, because it is like this, that the equivalent force is acting here. The equivalent force is acting here, where this distance is twice L by 3 and this distance is L by 3. Okay, you also understand that it is very much possible that the triangular load is like this. where the left end is the highest. Okay, in that case, what do you think? It will be just flipped. Okay, just the reverse of what you are having. So in that case, the equivalent force would be like acting like this. This distance would have been L by 3 and this distance would have been twice L by 3. Okay, so you make these kinds of little adjustments. Now you see, we have done quite a few conceptual cases. First of all, we took this kind of uniformly distributed load. Now we have taken this kind of triangular load. Now, if we go back to our tutorial sheet and look at this thing, look at this example, this problem. Okay, question number 3. Here you see that there is a combination of uniformly distributed load over this part and a triangular distributed load over this part. So this is like a conceptual combination of the things that we are doing here. You tell me quickly whether this is a statically determinate problem or an indeterminate problem.
Determinate.
It is very much a determinate problem. The only apparent complication here, it is not even a real complication. Apparent complication is that this is an overhanging beam. Okay, but nothing to worry about that. Okay, this overhanging part of the beam does not change the nature of the statical determinacy of the problem. Just as before, all the other examples that we have been taking up, here also you will have two reaction forces, one in the horizontal direction and one in the vertical direction. And one from this roller joint here or roller support here, you will have one vertical reaction force. Effectively, you only have two unknown reaction forces, the vertical one and the vertical one here, because the horizontal one at A, that will come out to be 0 because there are no axial forces acting over this beam. Okay, so again, I'm telling you, you just apply for this kind of a problem, and I'm not going to do this. Okay, I just kept this problem written down here to remind myself that yes, this question number 3 can be done just from a direct application of the kind of things that we have been discussing up to this point. Okay, so it can be done, but it is your duty to actually do it. Okay, please never underestimate the importance of any problem just because you think that you conceptually understand it. There is a massive gap between conceptually understanding something and actually implementing it. As an engineer, you must never underestimate the importance of actually implementing things. Okay, this is the most important lesson that you can take away from all your engineering education. Conceptually understanding things is certainly the first step, but unless you can actually implement it and bring it into manifestation in the real world, the job is not done. Okay, so the kind of things that we're doing, solving the individual problems, that is like an important intermediate step. Next step would be to actually designing it and finally to actually bring it into existence. Okay, so at this point, I will just take 2-3 minutes break, maybe 2 minutes break, because we have lost a little bit of time, and then we'll come back after 2 minutes to start solving these problems. Okay. Okay, let us start again. So this is the first problem from our tutorial sheet. Now, unlike the kind of things that we have been discussing till now, which were very much shaped like beams, this is in the form of a pipe, but you can of course imagine it to be like a beam, and conceptually there is no difference. However, just by looking at the diagram, it is not apparent to us if there is any kind of transverse loading on the beam. Transverse loading means this is the longitudinal axis, the horizontal axis of the beam. It is not immediately apparent where or how any force is acting on it perpendicular to that horizontal axis. because that is the kind of problems that we have been doing conceptually till now. There is some kind of distributed load or some kind of concentrated load, but here apparently there is nothing like that. So what is going on here? Tell me.
So, like because of that 5 kilonewton force, there will be some forces at the point C and C.
Yes.
What it's called.
Yeah. So not to worry. It is exactly. I mean, again, I am telling you this problem. The intellectual effort involved in this problem, the bulk of it has to do with what you studied in your first year. So at the point C, you have a hinge joint or a pin joint, and there you can understand that there will be a reaction force like this. Okay, so C vertical and C horizontal. There is a roller joint present at this part, and that will be exerting a let's say this is A vertical. That's a roller joint, so there is no horizontal force from that end, and there will be this external force of 5 kilonewton, which I'm representing by this P. Now, this is a very simple diagram. You can immediately understand that the value of this CH will be equal to P from a sigma fx equation, sigma fx equal to 0 equation. You will also understand that AV must be equal in magnitude to CV from a sigma Fy equation. But what are the values of them individually? That we do not know. So what do? We'll appeal to the moment balances, right? So tell me what I should do here.
So since AV is unknown, we can take moment about the point A.
We can take the moment about the point A. All right.
So C will be
better
more.
will be C.
So C will be more better.
C is also
because
better.
one force will be
Yes.
there.
C is the better
What?
C point, because then we'll have only the only unknown force will be the
Okay, whatever. But there is one slight complication left. Can you identify it? Let's say that you find out this A, B, and CV, all that you do. There's one slight complication left.
So we get a couple due to P and CH.
Yes. Not due to P, because P is actually acting through the horizontal axis. But due to this CH and
Say
CV.
AV and C.
So AV is passing through this point only. Okay, there is no problem there. Okay, but there will be a contribution due to this CH. So this situation is very much like that extra little frame, that inverted L-shaped frame that we did earlier. It is very much like that. So what you can think of is that you can try to translate this CH to this point B. Okay, so the point B is here. You can try to translate that CH to this point B, and that will result in a couple in which sense? So if you try to remove this CH and bring the CH
Clockwise.
here, very good. There will be a clockwise movement here. Okay, so this M is due to the CH. All right, so as soon as you do that thing, then it becomes like any other problem. Okay, you may as well forget about the individual contribution from this CH and this P, because what you are really bothered about, let me draw a clean figure here. What you are really bothered about as far as the shear force and the bending moment diagrams are concerned is this picture. You may notice that I have very easily translated this CV from its original point of application, which was up at this point, down to this point B, where this point B. Okay, it really does not matter because it does not contribute any extra couple, unlike the CH, because there is no moment arm with respect to the point B as far as the placement of this CV is concerned. But you will end up with this MCH. All right, now you can do this problem like you can place your X at this point only. There is no need to start from this absolute left end. You can start from X equal to 0 here at this point and proceed up to this point B. So this between A and B is where you are expected to find out the shear force and the bending moment diagrams. Okay, so just quickly tell me what should be the so I'm skipping a couple of steps here. Tell me what should be the bending moment, the shear force diagram look like.
The straight line parallel to x-axis.
Straight line parallel to x-axis. Should it be up or should it be below?
Sir, in the negative sense. I mean, minus V.
Yeah, so what we are basically doing is taking a cut section like this, considering the cut part to the left of it like this, where this force is like this, okay, this AV. Please note that I have taken it absolutely at the left edge because I am effectively considering the beam from this part, okay. So there is, you're basically neglecting this little screw part. Now, this force is V, this moment is M. So you are effectively doing this, that V plus AV is equal to 0 and V is equal to minus AV. You will of course find out that this AV, the answer to it comes out with a positive sign, okay, which is why when you draw the shear force diagram, this V, since it is coming out to be minus of AV and AV itself has a positive value, so it will come out like this. This is the shear force diagram, okay. So this value here, this is minus of AV. What is the bending moment diagram?
So minus X.
Minus slope, negative slope, passing through origin.
Passing through the origin, very good. So this is M. What is the value at this right end? What is the value at this right end?
5 into 80 into 10 to the power minus 3.
I mean, so what I wanted to say was minus AV into L. Okay, so this entire length is L, that is given as 400 millimeters, all right, but this is the AV force, okay. All right, so that's it basically. All right, of course, in a real situation, you will have to write down these things properly, okay, not skipping steps like I have done, so you understand. Okay, next we have another apparently complicated looking situation. Now you see, in each of the problems subsequently, I will not go into the actual drawing of the shear force and the bending moment diagrams. Rather, each of these problems I have selected because of a certain characteristic feature which I thought would be important to highlight to you. Drawing the shear force and the bending moment diagram, that is certainly the most important objective here. That is what you have been asked to find out in each of the problems. But like each problem has a certain important feature associated with it. That important feature I would like to highlight. Okay, that's the motivation why I have selected among the various problems available in different textbooks. I have selected these particular problems. I would like to highlight why these things. Now, for this kind of a problem, it is obvious that this is an important mechanical engineering situation. I mean, what could be more mechanical engineering than an industrial robot? Okay, so somebody was saying something. Please tell me.
So actually, I was asking for the answers of the tutorial sheet. So actually, how should we understand that our answer is correct or not? So,
okay, I'll try to come up with something. Okay, so I'll try to see if I can incorporate the shear force and the bending moment diagram somehow in the tutorial sheet itself. Okay, but you have to give me a little bit of time. Right.
yes, sir.
Sir,
In fact,
sir,
in the tutorial sheet, there is also mentioned that students are encouraged to plot the shear and moment diagram using computer programs.
Yes.
So can you tell that which computer programs we have to do that? Yes, it can be helpful to us.
So many of your seniors, they prefer to do it in Python because the advantage is that if you learn a little bit of Python, it actually helps you. First of all, you can write in your CV that you know Python, and then it actually helps you during your when you go for internship interviews and later on placement interviews. If it shows that you know Python and you have done maybe a number of problems and projects using Python, it kind of creates a good impression, at least in the current job market. Okay, and one of the biggest advantages of Python is that you don't have to, do anything like an illegal software download or anything. Python is actually free and open source. Download it properly, freely, officially, and do it. And there is extremely good support online. Like innumerable YouTube videos are present. I have also made a couple of videos for some of your senior batches. You can take a look at those. But anyway, I mean, you will find millions and millions of help online. Okay, so it's a good thing. It's a good thing. So I personally like to use the platform of Jupyter Notebook, but you can use whatever you wish. Okay, you can use PyCharm or whatever you would. It doesn't matter. Okay, I like Jupyter Notebook because the way Jupyter Notebook is designed, it is very easy for teaching purposes. Okay, I can write comments in between in a very nice documented way, and then also simultaneously do the problem. I personally like that. Okay.
sir,
Yes.
sir, in the previous problem, sir, could you please scroll down?
Yeah.
Sir, so the AV force was acting downwards on the beam. So, sir, in according to the sign convention, we should take it to be negative and then minus AV would be positive. So, why don't we consider any sign convention, sir, in this kind of?
No, you can take a sign convention like this, that when you are writing this equation, instead of doing like this, what you can do is you can formally write it like this, that sigma Fy equal to 0, and you take the upward to be positive. Okay. Now what will happen is that you see your V is downward, your AV is downward. Then minus V minus AV equal to 0. But at the end, you will still end up with V equal to minus of AV.
Okay.
Okay, enough.
Sir, I also have a doubt.
Yeah.
Yes, sir, I also had some doubts on previous problem.
Your voice is absolutely breaking up. Yeah, tell me once again. Hello.
Yes, now it's clear, sir.
Yeah, tell me.
So in previous problem at point C, sir, why can't we consider why we only consider the torque due to AV, sir? We can't consider MCH.
I don't understand what you're talking about.
Sir, at point C, there is a shearing moment, bending moment, and the torque due to AV and moment MCH, sir.
No, at the point C, there is only one horizontal reaction and one vertical reaction. When we translate that CH to this point B, there it contributes this MCH due to equivalent force couple system. At the point C, there is nothing. There is no couple there. There is only a CH and CV, exactly like first year funda, because that is a pin joint. When we translate this CH to this point B, then you have to write this CH together with an equivalent couple, because it's an equivalent force couple system, like, right? That is how this MCH is appearing.
Okay, sir.
Okay. All right, let's come to this problem. So you take a look at this diagram. You have this arm here, which is holding some kind of a load, this robot arm. There is, it is pin connected at A, no problem there. And it is also connected to a hydraulic cylinder, which has been mentioned very importantly to be a two-force member. So this BD, that is a hydraulic cylinder. Now, it has been further mentioned to us that the arm and the grip, they have a uniform weight of 0.3 Newton per millimeter and support the load of 200 Newton at C. So effectively, what we are supposed to do here is to consider this robot arm to be like a beam, and then consider the various kinds of forces acting on it. So effectively, again, I'm telling you that our intellectual effort, it boils down to solving this first year mechanics problem. Once we figure that out, once we figured out the reaction forces and all the various kinds of loadings on it, then it just becomes a matter of systematically going from one end to the other end, just being careful to find out the expressions of the shear force and the bending moment, and then draw it just carefully. Okay, it is just a systematic procedure after that, but the real intellectual effort involved here is to actually find out the reaction forces and the various kinds of loadings. So first of all, very clearly, it has been mentioned that BD is a two-force member. So the only possibility is that you have a reaction force acting at the point B in this fashion. So this is the force BD. Furthermore, it has been also mentioned to us that the arm and the grip, they have a uniform weight of 0.3 Newton per millimeter. Uniform weight means that you can consider that there is a uniformly distributed load of that much intensity, 0.3 Newton per millimeter. So this is like our W. What else is there?
Reaction at A.
Reaction at A and force at C.
Reaction at A and force at C. So let me draw this force at C. So this is, let's say this is P. P will be equal to 200 Newton. And at A, what do you think the direction should be?
So we take the components simply.
Yeah, we can take the components simply like this. So, all right, since you're saying, let me take it to be AH and A. So A vertical and A horizontal. What do you think the A horizontal should be equal to?
That FBD cos.
Component of BD.
Yes, yes.
BD
So
cos theta.
AH, the only chance for AH to be balanced is by the horizontal component of this BD force from the two-force member BD. Okay, and it's a good situation for us because this angle and all the geometry and everything is available to us. Okay, so all that you have to do, first of all, so let me not tell you, you tell me what I should do.
So
we first find all the unknowns.
Find A, B.
No,
by considering the
very specifically tell me about which point I should take moment, what I should do, what I should not do.
Sir, consider moment
So
at
first
point
of all,
A, then we get FBD.
First of all, I will write sigma fx equal to 0, and then I will obtain that AH will be equal to BDX. Okay, I'll just put it like that. Now you tell me. Yeah.
So moment at point A is 0.
Moment, not point at point A, say it properly. Moment about point A.
Okay, sir.
Moment about point A should be equal to 0. Okay, that will give us something. What will it give us?
So it gives us the force FBD.
It will give us the force FBD, right? So from here you will be able to obtain BD. Next, what are we supposed to do?
Then we take sigma Fy equal to 0.
Very good. Sigma Fy equal to 0. What will that give us?
The vertical component at
Yes,
point A.
AV. Done. That's it.
Now we will separate into A, B
Yes.
section. And B
Now
section.
geometry is given, you proceed from the left hand side, go to the right hand side. I mean, of course, it's a messy looking situation, horrible looking situation rather. And I can tell you the shear force and the bending moment diagram does not look cute. Okay, it's rather complicated, but it's just a matter of investing the time to do it correctly. So effectively what we are looking at is this kind of a thing. For the shear force and the bending moment, okay, I'm not actually drawing the free body diagram now. I'm actually drawing the thing which will enable us to draw the shear force and the bending moment diagram. So here you are taking the vertical component of this BDY. You are taking this distributed load, uniformly distributed load. Magnitude is given to us, and let us not forget we have this force B also. Okay, so you go from this part to this part. There will be the contribution from the AV, there will be the contribution from this distributed load. Then you go from this point to this point, there will be the contribution of this one, this distributed load also. That's it. Okay, so conceptually
0 to point A.
0
from
to
0 to point A, there is no load, so
yeah.
It will be 0.
Okay. In fact, I would say that you don't even have to start from that absolute left hand side. Okay, just like in the previous,
Excuse me, sir.
neglected it, you can neglect that part. You can start from this point A and go up to this point C.
Sir, there is a load from 0 to point A. The weight of the rod.
Oh, sorry.
0.3 Newton per mm.
Yeah, you're absolutely right. 0 to A, there is a point. So I should draw this correctly. Thank you for pointing that out. Thank you. Very bad, silly mistake from me. So it should be like this. Thank you. Okay, so from 0 to the point A, there is this distributed load. Okay, so the shear force there will look like a linear thing, linearly increasing thing. Okay, so the V will be like a minus Wx there over that thing, and the M will be minus Wx squared by 2 from 0 to this A. Okay, and then you can proceed. So I will not repeat, go into all those details. You can figure that out, and I'll try to give you the diagrams also. Okay, let us proceed to the next problem. Again, I have selected this problem for a certain reason. We are not going into the actual drawing of the shear force and bending moment. So we have a beam which is bolted at the point A, and it rests on some kind of a bearing support. Okay, bearing pad at B. Okay, this is a bearing pad that exerts a uniform distributed loading on the beam. This is the reason why I have selected this. All this while, the various kinds of supports that we have taken either have been fixed ends, like in the cantilever problem, or they have been like simple supports or roller supports, things like that. But this is a different kind of support. It exerts a uniformly distributed loading. See, in practical terms, this is not such an unusual thing. It just means that this beam is lying flat on some kind of a ground or soil or something like that. Okay. But of course, in terms of mathematically representing it, we have to be careful. And overall, it has been mentioned that the beam is subjected to this uniformly distributed load of 30 kilonewton per meter. So now you tell me very quickly, what should be the diagram be looking like? Tell me. I will first draw the easiest thing. Uniformly distributed load. Okay. At the left end, at A, what should be the things?
Horizontal and
vertical reaction components.
This, of course, the H is going to be equal to 0. What should be this thing? From
Uniform
this bearing,
distributed load pointing
uniform
upward.
distributed load that has been mentioned to us, right?
Sir,
So yes.
will there be no moment at A?
No. At A we have a pin joint. That's a pin
Okay,
joint.
sir.
Right. It's mentioned, no? The beam is bolted or pinned at A. So maybe this bolted part was a bit of a confusion, but you can rest assured that there is no moment at A. All right. So we have this distributed load due to the bearing pad. But the thing is, this value is not known to us. All this while, whenever distributed load was occurring, we had the information about its intensity, but now we don't know. But nothing to worry. You just treat it like a simple mechanics problem like first year. Do it. Okay, so see, again, we don't know the value of this AV. We don't know the value of this W. Only problem here is that this is distributed. So what do? You can take the uniform, like the equivalent force due to this. So this is over this distance of 0.6 meters. Okay, so W into 0.6 meters. That is the equivalent force. And that force is acting at a distance of 0.3 meters from the point B. Okay, so this distance here is going to be 0.3 meters. Okay, so with this information, all that you have to now do is to take the appropriate moment balances and force balances to determine the unknown reaction forces. So what will you do to find out this W? Tell me.
So we will balance moment about A.
About the point A. Very good. So sigma MA is equal to 0. And then let's say this is given to us 30 kilonewton per meter. This is like Q. Okay, so all that you have to do is, write these things properly. Just quickly tell me what it should be.
W into 2.7 into 0.6.
Tell me due to this 30 kilonewton per meter starting from that. So it should be 30 kilonewton.
30 kilonewton into 1.5.
Into no, do it
2.4
into 2.4 into
1.5.
1 point.
It will be 1.2 plus
0.3.
Okay, this is a meter and this is a meter. All right, and this is positive or negative. So if I take this anti-clockwise to be positive, this is clockwise. So it should be minus.
Negative, sir.
Yeah. And then the contribution from the W. What is the contribution from the W? It is W into 0.6 meters into this distance 0.3 plus 2.4 plus 0.3. 3 meters.
3.
Yes. Positive or negative?
Positive.
Positive.
Equal to 0 or what?
0.
Yeah.
Yes, sir.
All right. So from here you can find out the W. Okay. And then after you have found out the W, all that you have to do, so this will give you W. And then you just do this sigma Fy equal to 0. This will give you the AV. And now you have everything that you need. Just proceed from the left hand. Be careful, find out the answer. Okay. That's it. Anything that you want to ask from this problem?
Sir, in general, sir, that bearing pad can exert a slight in inclined direction, that force, due to frictions.
It can, but here it is just, it has been mentioned clearly, that it exerts uniformly distributed loading. Okay.
Sir, I want to confirm one point.
Yes.
Sir, while drawing the bending moment diagram and shearing
Shear force diagram.
diagram, then we need to consider it as a distributed force, right? So we should not convert it as an equivalent force.
Yes, yes, yes. Very good. Very good point. Okay. Very, very good point. I actually wanted to mention this, but I forgot. So see, for the purpose, everyone please listen carefully. Okay. Very, very important point. For the purpose of finding out the values of the reaction forces, we are taking these kinds of equivalent forces. However, if or when you are actually drawing the shear force diagram, okay, when you are actually drawing the shear force diagram, you have taken an X, and suppose you have finished drawing the shear force diagram, whatever the way may be, starting from the left end, you have taken from here to here, and then you have gone from here to here, you've gone from here to here. Let's say you are working between these 2 points. Now, you may be tempted to proceed like this, that this is a force Q acting over this distance of 2.4 meters. What I will do is I will take an equivalent force like this. I will take an equivalent force like this at a distance of 1.2 meters from this point, or 1.5 meters from the point A, and then this becomes even simpler, and I will proceed to draw the shear force diagram. If you do like that, if you proceed to the shear force diagram like this will be completely wrong. Do not do like this. Rather, you are supposed to proceed from the actual distribution of forces. The actual distribution of forces like this. Why it is important? Because you see that if you have a beam like this, if you have a beam like this, and there is a concentrated force like this, suppose it is like this, then if you take a cut section here, then the shear force in this region, that is a constant value because of the V being balanced by this reaction force. However, if in the place of this you have a distribution of force, like this, then the situation as far as the shear force diagram is concerned, it is completely different. Meaning to say that if you take a cut section here, you will have definitely the contribution from this reaction force, from this leftward reaction force. But as you proceed by increasing X value over this distance, there is an increasing contribution from the intensity of the force as you proceed from left to right. So the V force that is going to increase linearly in this, if you do it properly here by taking the distribution. But if you go back here, it may seem to you that this force is the equivalent of this force, so there is no problem. The problem is that in the correct representation of the shear force diagram. Okay, as far as finding out reaction forces is concerned, that is fine, doing it like this. But for shear force diagram, you actually have to take the real distribution of forces and draw the shear force corresponding to that. So this thing will be wrong and this thing will be correct. If you draw the shear force corresponding to the actual thing, only then it will be correct. Okay, so please do not forget this. So very, very good point raised. Okay, next thing. Another problem. Again, as far as the shear force bending moment concerned, it's not a big deal here. Okay, it's even easier than the previous problems. It's certainly much easier than question number 2. But there is a special thing going on here, which is why I selected this problem. So we have been asked to find out the shear and moment diagrams for the beam when the support at A, you note this part, okay? When the support at A allows it to slide freely along the vertical guide. This is very important. There is no resistance to the vertical movement of the end or the left end of this beam. It can slide freely along this. So it is like, I mean, the way that has been drawn is very nice because it gives you the correct impression that you would expect from a roller support. So these are like rollers. These are like rollers. They do not offer any resistance to the motion parallel to them. Motion parallel to them happens to be the vertical direction as far as our diagram is concerned. So there is no resistance to the vertical movement of the beam on this end. What is the implication of this? Implication is that usually when we have simple support or a fixed support or a clamp support, we have a vertical reaction force at that end. What I mean to say is that suppose you have a beam like this, time and again we have seen that when you have a simple support at this end, or perhaps it is a cantilever beam where there is it is fixed to a wall here. In all these cases, you remove this support, and then you equivalently represent them. So you remove this support and you represent them by some reaction force like this. Here also you will remove this wall and you will say that there is some kind of a vertical reaction force here, a horizontal reaction force here, and for a fixed wall you'll also have a moment. But here, tell me what is the difference? Because there is no resistance to the vertical movement, there will be no vertical force here. Okay, that seems very non-intuitive. Like you have a beam which is being subjected to a vertically downward acting external force, and at this end where it is supposed to be supporting it, it is not even giving any support in the vertical direction. It seems a very non-intuitive kind of situation. So what is going on here?
So there should be moment so that it can suspend.
Yes, there should be moment. And why do you think there should be moment? What is it actually which is the background to this moment?
So that vertical walls.
The rod.
Please say that again. Not here.
Normal force from walls.
The normal force that is exerted by these rollers on this beam. Normal force means force in this direction and force in this direction, or the opposite direction. Okay, I mean just the vice versa of the directions that I have drawn here. So those kinds of forces, they will ultimately give rise to a couple or a moment which will be acting on the left end. So whenever you have a support like this, you understand that there is no vertical force. So vertical force absent. Horizontal force may be there, but as far as the solution of our problem is concerned, in which we are definitely concerned about the transverse loadings, the vertically oriented reaction forces, and definitely the moments, it is that moment part which will be of concern to us for solving this problem. And of course, at the right end, since you have again another roller support, you will have a reaction force in the vertical direction. So overall, the diagram will look like this.
Excuse me, sir. So actually
Yes.
I have one little doubt. So actually in question it is said that means it can slide freely along the vertical guide. But sir,
Yes.
there should be at least one thing, means one support is needed to sustain in vertical, means in horizontal direction for that beam. Because if
there is one force required to support the beam in the horizontal direction.
Means there should be one reaction.
No, there will be reaction forces in the horizontal direction.
No, I'm talking there should be one reaction which should be in vertical direction. So
There
how
won't-
it can?
There won't be. Yeah, that's what I'm, you see the diagram, you'll see. Okay, so suppose I take a moment like this and don't draw anything else here. You can draw a horizontal force, it doesn't matter. Okay, because sigma fx equal to 0, whatever the distribution of horizontal forces from these rollers, they will internally balance each other out. Okay, so that's not a big deal. But suppose I just stop the free body diagram at this point. Okay, So I just say that this is MA. You are saying that there must be a vertical force here for this thing to be in equilibrium. Meaning that if I do not draw this vertical force at this end, this thing will not be in equilibrium. But suppose you find out that this thing is actually in equilibrium just by the consideration of this MA and this RB, now this W is of course there, then will you not be sure that yes, it is working?
Yes, it will be.
Yes, RB will be equal to
Understood.
W.
Yes, so that is why I said no, that this picture, it looks a little bit non-intuitive. I mean, it will take you a while to wrap your head around it. Why it is like this? But it actually works.
Sir, I have a question, sir.
One more thing, okay, because I'm running short of time, I just want to mention something. So this kind of a thing, which here it has been depicted to be present at the wall, it may also be present in between the beam. Okay, so I'm saying something besides this problem. So it can be something like this. That suppose two beams are present. Two beams are present like this. And they have been joined through some kind of a special arrangement where the interaction between them is through some kind of rollers. So there is no resistance to the vertical movement of these two beams side by side. But you understand that there will be a couple associated or arising because of the normal forces from these rollers. Now this kind of a situation where you do not have the presence of any vertical force, it is sometimes referred to as a shear release mechanism. Shear release mechanism. Why it is referred to as a shear release mechanism? Because you understand that this shear, it is like a vertical force. Since there is no vertical force here, it is like all the vertical things that are happening, it has been released. Okay, it has been set to 0. Here also, the vertical force, it has been, because of this special arrangement, it has been set to 0. So that it is like this, that had it been like a cantilever beam, there would have been a reacting or a reactive shear force exerted by the wall on this beam. But that reactive shear force is not, it has been removed by the presence of this kind of a roller mechanism. So it's like a shear release. And whenever the condition of shear release is present, the V at that point is going to be equal to 0. Just like you'll see that at this left end, the V will be equal to 0. So also if you're having this kind of a roller interaction in between the beam, at that point also V is equal to 0. Now you tell me, this shear release thing or this release business that we are talking about, you have actually encountered this earlier in your first year also. I'm telling you how. Have you not seen two beams which are connected by pin joints? You have seen this many times, various kinds of complicated situations were there. Okay, this kind of a pin joint you have seen. At this pin joint, what is happening? What is 0? At that pin joint, what is 0?
Moment.
Moment is 0. Okay, so at this point, you have moment 0. So M is equal to 0. Okay, at this point. So what do you think should be the terminology here? This kind of an interaction between two beams where the moment has been ensured to be 0. If this was shear release, what it should be here?
A bending release or something like that.
Yeah, it is actually called moment release. So if you have this kind of a configuration, then if you want to draw the diagram, this will be like at that point of X, the moment will be equal to 0. And I'm seeing that it is 10:01 by my watch. So please all of you quickly leave and go to your next class. Okay, whatever doubt you have, we will address in the next class tomorrow. Plus you can post in the discussion channel. I'll try to come back to it and see. But everyone, please leave immediately. Bye bye. Thank you. Thank you.
Thank
Bye
you,
bye.
sir.
Thank you, sir.
Yeah.
Thank you.
Go quickly.
Thank you, sir.
Yeah. Thank you.
Thank you, sir.